We have following task: generate Cartesian product from vector of integer lists, and that's the description. Given a vector of integer vectors, so our input is a vector of vectors, or 2D vector, if you wish, and our task is to generate all ordered tuples, and ordered, this part is meaningful, by choosing exactly one integer from each inner vector, and that's so-called Cartesian product. Yeah, so we'll have one big vector inside subvectors, and we construct the result by choosing a single integer from each of the subvectors in the input. Okay, so the first integer from the first, then the first integer from the second, and so on. Each time we choose one from each of the inner those subvectors from the input, and we put them together as one part of the subresult. And of course, we can mix them up, but still following order, meaning that the one that we choose from the first subvector comes always first before the one that we choose from the second subvector, and so on. So that's that Cartesian product, and you will see an example which maybe will help to clarify it a little bit more. But we have some constraints as well. Each inner vector will contain distinct integers, so we don't have to worry about repetitions within the subvectors, and the number of inner vectors is at least one. We don't have to assert or do any kind of weird ifs. If empty, then don't know, throw an exception or something like that. We don't have to worry about this. There will be at least one inner and at most 10, meaning that there won't be that many of them. And again, for each inner vector, there has to be at least one number, at least one integer inside, and at most 10 integers. And that's good because we can also do a recursive approach, which is a little bit easier, maybe, or simpler to understand. Like, it's simpler to write and easier to understand than the iterative one, at least for the most people. And the iterative one usually takes less RAM. Yeah, so if we have very big inputs, then probably you will have a Stack Overflow exception when you try to do a recursive approach. But in this case, we don't have to worry about that, and we can compare both approaches. And here is an example. So we have those inner vectors, 1 and 2. That's one inner vector, then 3 and 4, 5 and 6. And how do we construct the result? Each time we choose one number from each inner vector. Yeah, so for example, 1, 3, and 5. Those are those 1, 3, and 5. 1, 3, and 6. That's the next option. 1, 4, and 5, and so on. And I hope you get it by this point. So each result or sub-result will have as many elements as there are subvectors in the input. And we have place to fill in for 2 solutions. So one will be recursive. This one we'll do first. And then we'll do iterative, and we can compare both of them. And then there are some test cases to test our approaches, both recursive and iterative. And the first case is the one that we just discussed. So 1, 2, 3, 4, 5, and 6. Then there is a single list case when we have just a single subvector. And then there are all singletons, meaning we have many subvectors, but each of them has exactly one integer inside. And then there's empty input, which should result in the product of 0 lists. Yeah, and we'll have just an empty vector of vectors. Yeah, which will have one empty vector inside. That's the result. So now let's start with recursive solution. We will have the main public method or the public function, Cartesian product recursive. But to make things easier, we also will use this helper, which will implement the recursion itself. Yeah, so here it's just our wrapper and the public function, which will create all the necessary things, and then all the magic will happen in the helper. So let's start with the wrapper or with the public function, and let's create the output vector of vectors like this, and let's call it results, and we return by the end results. Then we will need for each result there will be an inner vector that will fill, and we will call it current. And then maybe first let's reserve memory for current. But in this case, it's not really that necessary since there will be at most 10. But to be polite, or maybe to be more correct in C++ terms, we can reserve as many elements as there are subvectors in the input. As we said, each time each sub output will have as many elements as there are subvectors in the input. And then we call the product helper product helper, and we pass the input, then we pass the index, we start from 0, then we pass the current and the results. Yeah, so far so good. Nothing has happened yet. And here we will use so-called backtrack. But first, let's do the easy stuff, which is the base case, where we already reached all the elements for the current subpart, which we will have, in this case, we had each time 3 elements, but in general, we want to have as many elements as there are subvectors in the input. Right, so we can check like this. And return and add it to the results. So pushback current. Okay, and now let's loop through each number in the input. And let's now first push back, not to results, but to the current. And sorry, not the whole input, since the input is the list of lists or the vector of vectors. Input on the index, that's what we use the index for here. So we'll go one by one. And here we have to put the number, and that's the backtracking part. First we put it, then we call it recursively, and then we pop back. And here, product helper of input index +1, current, and results. And this is the whole story or the whole magic behind the backtracking. So now let's save it, and now let's try to compile. And 51, I had some spelling error. Vector. And that's it. And we pass all the cases for the recursive stuff. So now let's do iterative. We go down. Of course, we have to also create a container for the output. And we can call it results again, but we'll put at least one empty list or one empty vector inside. That's because our approach here will be a little bit different than what we did already above. and you will see in a second why it's needed. We'll iterate through each subvector of the input. So far, so good. And then for each subvector, we'll create again the same thing as we had above. So a vector of vectors. And we'll call it TMP because we will be iterating through the results that we already have. And then we will store the new results in the TMP, and then we will replace it with the final results. And we'll see in a second. We can reserve the memory here, and we need as much as we already have times the size of each vector. And now we can iterate through each prefix in the result. Since before we were creating like one subpart by one subpart, and adding them to the result. Let us go here. Yeah, so each time we were creating one of those subparts, like this 1, 3, and 5, adding them to the final result, and that's it, until we have all of them. But this time, we will be creating just one element of each subpart all the time, in each iteration. And we'll have all the subparts, but not full. That's why we call them prefixes. And that's it. And now we can iterate for each number in the current vector. Const auto out. We will emplace back TMP emplace back on the current prefix. Yeah, and then to the current prefix we will add pushback new number. And after we are done with this, we will swap with TMP. Okay. Let's clear and let's compile again. So Cartesian product. $67, and it has to go on the other side. And this, and everything passes successfully.